Problem number 1 on the sheet says a proton traveling to the right along the x-axis enters a region where there is a magnetic field of magnitude 2.5 Teslas directed upward along the y-axis. If the proton experiences a force of 3.2 times 10 to the negative 12 newtons, first find the velocity of the proton, and then part B, then determine the radius of the circular path that it would follow while in the magnetic field. So the first thing is we're going to find the velocity. This is a charged particle moving through a magnetic field. And so remember, if I want to find the force on a charged particle moving through a magnetic field, that's QVB sine theta. More times than not, that's going to be 90 degrees. It does say directed perpendicularly, or one's x-axis, one's y-axis, and so that's going to be 1. So I'll go ahead and just say that's 1 right now. And I'm looking for the velocity. Now we can go ahead and put absolute value on the Q, but it doesn't matter because this is a positive charge anyways, being a proton. And so V is equal to FB, the magnetic force, all over Q times B, because I'm just going to divide both sides by QB. That'll cancel with that. But if I do that to the right side, I got to do it to the left side. And so I could plug in. My magnetic force is 3.2 times 10 to the negative 12th newtons. All over Q, it is a proton. So a proton has a charge of 1.6 times 10 to the negative 19th coulombs, and then the magnetic field is 2.5 Teslas. So if I punch that into my calculator, I should get an answer of 8 times 10 to the 6th meters per second as my velocity. So that's how fast it will be moving. Then it says determine the radius of the circular path. Now remember, if it's moving in a circular path, there is a net force because it's changing direction, but it's not speeding up. We're going to assume it's not speeding up, so that's MAC. It's FB, which is causing it to move in a circular path, is equal to mv squared over r. And so I know everything now. I'm looking for r, so r is equal to mv squared all over FB. This is the mass of a proton, so that's 1.67 times 10 to the negative 27th kilograms. My velocity is what I just got to be 8 times 10 to the 6th meters per second. That is being squared. And then FB, once again, is 3.2 times 10 to the negative 12th newtons. And so I should get a value of 0.0334 meters. And so when we move in a magnetic field, we're going to move in a circle. The cool thing is a magnetic field can actually cause me to speed up. It can only cause me to change direction. And so I won't speed up. So that means I only have centripetal acceleration to move in a circle. So now problem number 2, it says 2 long straight wires with a linear mass density of 0.0850 kilograms per meter. So that, remember, that's lambda. That's the same thing as saying m per unit length is equal to 0.085 kilograms per meter. They're hung from a pair of massless strings. So this string here, we're affixed on the ceiling. This string is massless. Right there, as shown from an end-on view. So this one has current coming out. I'll go ahead and write that's coming out. You see the dot, and then X means in. So they're basically parallel wires. Like if we were looking at them from the side, we'd see the parallel wire, but it's been rotated so that we see it in and out. The wires conduct equal currents in opposite directions. What do we know about wires that carry current in opposite directions? They repel. So actually, these guys would just be sitting there, and all of a sudden we flip current on, they'll fly away from each other. So initially, they were probably sitting at that location, and all of a sudden we flip current on, and they repel each other. Yep, so it says, so they repel each other right there. The force of their magnetic field opposes the tension that pulls them together. The current is adjusted until the strings reach a configuration shown, and the wires are in equilibrium. What is the current? Well, really quickly, this is kind of cool. If this is a 60-degree angle, and I connected these two lines with a line right there, if that's 60, and this length are the same, that's got to be 60, and that's got to be 60. So this is a equilateral triangle. So I know the distance between the wires right there is 2.5 centimeters just by looking at it. All right, so we have that value, 2.5 centimeters. What is the current? So we're trying to find I, okay? Well, this thing is just sitting in a current state of equilibrium. So what I'm going to do is I'm going to say sum of the forces is equal to 0. But I got to do that both in the x and the y direction. So sum of the forces in the x direction and sum of the forces in the y direction. But before I can plug into this, I need to draw a free body diagram. So let's just look at just this y right there. So I'm going to put a little dot. All right. The first force that's acting on them, of course, is gravity. That's acting straight down. So that is mg. All right. There's got to be a tension acting up and that is I'll just call it FT. And that angle right there is 60 degrees because of what's given. And then because they're opposite directions, there's something pushing them apart, and that is the magnetic force that they act on each other. So there's FB. All right, well, we're pretty good except for this guy right here. I'll go ahead and draw him in red. He's at an angle. So what I need to do is I need to find him in the X direction. So let's call that FT in the X direction. And then let's call this guy FT in the Y direction. Now, how do I go about finding it? Well, if I take a look, this is my hypotenuse right there, and then the other side. So FT and the Y is opposite, so that's going to be whatever the tension is times sine of 60 degrees. And this will be FTX, which is FT cosine of 60 degrees. All right, and so if I redrew this, let me go ahead and just come down here. We have gravity pulling us down, so there's mg. There's something holding us up. What is that? That is Ft in the y direction, which we know is Ft sine of 60 degrees. All right, we have the magnetic field trying to push us to the left. There's Fb. And then we have the tension trying to pull us to the right. That's Ft cosine 60 degrees. And so you guys are smart. That and that must be equal, and that must be equal. So let's go to the x direction. So here's the green. I know that FB, actually I'll just do it like this. FB in the x direction to the left has to equal Ft cosine of 60 degrees. And I'll just go ahead and write 60 degrees. And then in the y direction, I know that mg down has to equal Ft sine of 60 degrees that way. And so I can actually solve for Ft. Ft is equal to mg all over sine of 60 degrees. I just divided both sides by 60. And so that Ft can then be plugged in right there. And so I get FB is equal to mg all over sine of 60 degrees times cosine of 60 degrees. And just to make it easier, I'm going to go ahead and write this as mg all times a quantity of cosine 60 degrees divided by sine of 60 degrees. That's equal to FB. Okay, now that's the force between the two wires. Do we have an equation that relates the force between two wires, two current carrying wires? And the answer is yes. And so we know that the equation that I derived the other day, that FB equals mu naught, the current in one of the wires, times the current in the other wire, times the length of wire, all over 2 pi, and then d, the distance between them. So then I can say that and that are equal. So let's go ahead and say that. So that's mg cosine of 60 degrees all over sine of 60 degrees has to equal mu naught. Now I1 and I2, let's go back up here. It says that the current is adjusted until the strings reach the current friction right there, but I think it says that the current is equal. They're equal currents. And so I1 equals I2, which I'm just going to call I. And so that's I times I, which we've already done this, that becomes I squared all over, or all times L times 2 pi d. Okay? Now what I'm going to do, just for the sake of this, I'm going to go ahead and divide L first by both sides. All right, just you'll see what I'm doing here in a second. So I'm going to get m all over L times g. Now when I divide the whole thing by L, I can divide just one of the terms by L, and it's the exact same thing mathematically. Cosine of 60 degrees all over sine of 60 degrees. And that equals mu naught I squared all over 2 pi d. Now the reason I did that is because m over L is my lambda term. That's that linear density that we were talking about. I think I gave that expression to you, but I'm going to leave it as m over L. That's fine. So then to get I by itself, we're trying to find the current. I'm going to multiply both sides by 2 pi d all over mu naught. So that will cancel with that, that will cancel with that. But if I do that on the right side, 2 pi d all over mu naught. So I'm going to rewrite this again. So 2 pi times the distance between them all over this mu naught, the permeability of free space, times m over L term, times gravity times cosine of 60 degrees all over sine of 60 degrees has to equal I squared. So let's go ahead and solve for I squared first, then we'll square root that. So let's go ahead and plug everything in. 2 pi, the distance between them was 0.025 meters, because I think if we look up, it was 2.5 centimeters, so divide that by 100, so 0.025 meters, divided by mu naught, which is 4 pi times 10 to the negative 7th Teslas times meters over amps. Then I'm going to multiply by m over L, which is 0.085. So 0.085 kilogram per meter. Then multiply that by gravity of 9.8. So 9.8 meters per second squared, and then times cosine of 60 degrees all over sine of 60 degrees. And so I get I squared is equal to 60,116 point, let's just say 6, and that will be amps squared when I do that. And then if I square root both sides, I get that the total current needed for this particular case to be 245 amps. And so in order for this case, with these two wires with that linear density and that angle and that length of string and that separation, that's got to be an answer of 245 amps for our value.